Swayam Prabha. Digital India. Educated India.
I will be fine now. So we're going to continue session about characterization of materials. And yesterday we were talking about the complementary use mainly of Raman and infrared. We're continuing about that. And another aspect, always looking at the surface of the catalyst, you will see that we are getting very deep into the surface because most of the interactions typically occur at the surface of the catalyst. The bulk has a setting, but whatever this bulk is saying is reflected on the surface, which is where we interact with the molecules. This is why we have so much emphasis on it. Like for instance, we've seen that infrared is very good to observe the chemisorption of different molecules. It's not only infrared. Raman can also report on the chemisorption of molecules. This is true that the Raman signal is weaker, but you can still see things. For instance, in this figure here, you can observe the chemisorption of methanol at the surface of a silica-supported vanadium oxide catalyst. And on the left side, you can see the low frequency region around 1000. So when the sample is in oxygen helium at high temperature, it is just dehydrated. So you get the 1033 wave number, which corresponds to the vanadium bond mode of a supported vanadium oxide. But when you start to flow methanol, what you will observe is the onset of a new band at about 1030. That corresponds to the vanadium oxygen carbon bond. So that's a characteristic of alkoxide groups. It happens with methanol, it happens with ethanol, it happens with hydrocarbons. In the end, you are having a bond between vanadium, oxygen, and carbon at 1060, which is apparent here. Of course, if you remove methanol and you go back to only oxygen helium, that alkoxide group disappears. If you change temperature and you flow methanol again, you get it again. If you remove methanol, it goes out. And if you feed methanol, it comes back again. So this is something that is happening constantly, continuously. And the vibrations, well, here you have a quick summary on the right side for the Raman bands on the different catalysts at different conditions, mainly some of the vibration in the 2900 for the CH vibrations, and also down here, but these are mainly on the CH region, which is what I'm showing you here. And what is important is that when you are chemisorpting methanol, like in the case of infrared, you are getting a lot of information, because not only that I'm getting methanol connected, for instance, to the vanadium, and here you can see the VOC bond, but you can see that the methanol chemisorption in the CH region looks different about the frequency when you are absorbing methanol on pure silica than on vanadium silica. When there is vanadium, in addition of these two peaks, you get another two peaks. And these other two peaks correspond to methoxy groups on vanadium or methoxy groups on silica. And as you move here, you are going from bare silica to increasing content of vanadium oxide, from 1, 3, and 5 weight% vanadium oxide. So what happens is, as expected, that the bands associated of methanol sitting on vanadium with respect to the bands of methanol sitting on silica increase. So you get a change in the relative intensity. So you can really tell not only where that methanol is chemisorbing, but where it is chemisorbing. You can do that in Raman, and you can do that also in infrared. So this is what you see here. Even in more detail on that system, you can see here that the alkoxide group is not only showing a band at 1060, but also at 660. And quite often, for supported vanadium catalyst, when you get alkoxide with a hydrocarbon or with an alcohol, in the end you will have this bridging oxygen between the carbon and the metal. And vibrations will be around these two frequencies, 1060 and 660. And of course, depending on where they're sitting, you can tell like methoxy on silica and methoxy on vanadium, or zirconia, or titania, or ceria, or whatever the support is. So that is also very convenient, very versatile. You can do the same thing with infrared. Infrared will be very sensitive. For instance, here you have the methoxy species on gold supported on Syria. And again, you are observing different species, and as you are changing the conditions, you will see how one species are evolving into other species. In this case, they were doing an isotopic exchange, so you have like two kinds of carbon isotopes and the change of the frequency. But the point is that either Raman and infrared are reporting similar things. These kind of vibrations are the same. But there's something very important that you will see when I talk about what is special about Raman compared to infrared, is that if you want to look at a sample with these two techniques, it's for one reason, because they are complementary. Both of them give you molecular information. And if you're looking at chemistry of methanol, it will probably be similar, and you will say, okay, infrared is much more sensitive and it will report more nicely with a better signal. This is true. But you will see that in the case of Raman, it is more sensitive to polyolefinic carbon deposits, and that the infrared is more sensitive to oxygen-containing carbon deposits. So during a reaction, you have a carbon buildup of things at the surface. If you are only using Raman, you will essentially say, oh, I see a lot of polyolefinics, coke, polyaromatics, and whatever. And this is what Raman is reporting to you. If you look at the same sample with infrared, oh, I see a lot of formates, oxygen-containing things, because this is what infrared is reporting to you. None of them is absolutely right. We are describing the elephant from different perspectives. The nature of the carbon deposits is actually that you get some polyolefinic species and you get oxygen-containing species. And if you're only using one of these techniques, you will only get part of the reality. And you will make a story based on a biased information. So you will be biased because experimentally you don't see everything. So that's why this is very important. And we typically collaborate with a group of Marco Daturi in France on the Laboratory of Catalysis and Spectrochemistry, where we do a lot of complementary studies with Raman and infrared. Okay, so we were talking about supported oxides, and I was telling you, like, Raman is very sensitive for these materials. At low loading, like 1 weight%, you can very nicely see the molybdenum oxide hydrated and dehydrated. And in the case of alumina, you hardly get any signal from alumina, so almost everything you see corresponds to the surface molybdenum oxide. And as I said yesterday, this is a hydrated sample, room temperature, and this is dehydrated, so this band at 990 that increases to 1000 corresponds to the molybdenyl bond of supported molybdenum oxide. And if you remember, I was telling you how this band over here at about 800 corresponds to the bridging oxygens, molybdenum, oxygen, molybdenum, which is telling you that the system is getting increasingly polymerized. You put a little bit more, you will see molybdenum oxide crystals. So, and also even the Raman can tell you that the molybdenyl vibration for the isolated species is 990, at the polymerized is 1006. So even if you plot the frequency of the molybdenum oxide bond, you will see how the system is increasingly polymerized. Actually, I was looking for that figure that I had at some paper, where basically with the loading, and usually for loading, the units I use is molybdenum atoms per square nanometer. Typically, because in a square nanometer, you may have up to 6, 7, 8 atoms, depending on whether this is vanadium or whatever. So it's quite easy to remember. It's not 10 to the minus 28 or whatever. It's up to 8 atoms per square nanometer. So you are doing in a scale which is similar to the size of these moieties. Now, so typically up to 6, 7, you will get a monolayer. So actually the frequency of the molybdenyl vibration for the dehydrated samples will increase from 980 all the way to 1005 or whatever, little by little until it levels off. At that moment is basically when you get the monolayer coverage. And above that value, what you will get is molybdenum oxide crystallites. But over here, it will be isolated and increasingly polymerized. And the molybdenyl bond frequency will be progressively increasing, as you can see here, from 990 to 1006. Okay. Remember that infrared will not allow you to see things in such a detail. Okay, about the structure. Raman is also very informative about the structure of the material, even in something that was very interesting. That was a work made in the early 90s by Frank Hardcastle in his PhD with diesel wax. And that was basically a diatomic approximation, simplifying the whole system and focusing only on the metal-oxygen bond vibration, bond length, bond order. And they found this correlation for many compounds. Here you have it for the case of molybdenum and for the case of vanadium. But they reported that for, you can see, vanadium, niobium, bismuth, tungsten, phosphorus, and titanium compounds, where at least this correlation happens. So this is an experimental correlation where basically what they are observing is that for the frequency of the metal-oxygen bond, essentially corresponds to a given bond length. Of course, the higher the frequency means there is more energy, they are more strongly bound, and they are closer because there is a stronger attraction. And then you are dealing with, for instance, at about 1000, the bond distance is about 1.7, 1.8 angstrom. And as it goes weaker, means that the interaction is weaker, so they are at a bigger distance, and you are talking all the way up to 2.4 angstrom. That is quite similar to what they report for vanadium, and the same thing for these other elements. That's very nice. That's very convenient for one reason. How do you typically measure the distance between two elements? Which kind of technique can you use? Synchrotron-based techniques can tell you the distance between a metal, between one nuclei and another nuclei. X-ray diffraction can tell you these things. But all these things require that you have a crystalline material, requires that you get a beam time to access a synchrotron. And now these measurements you are making in a Raman system within seconds. And it is reporting, it is finding a correlation between this frequency and the bond distance with the quality of fraction of an angstrom. It's amazing. That's a very accurate system so that you can very simply estimate and work with these bond distances for many elements without having to have a crystalline material, without having to use a synchrotron experiment or whatever. And of course, they also found correlation with the bond order, whether this is double, single, or whatever. But this is a very important approach that from a structural point of view is very important. I believe you know what an anvil is. Well, like that one. When you are studying things at very high pressure, you have something which is called an anvil cell. So somehow is that the idea is that you are putting a very, very big pressure and that you can make a Raman spectroscopy inside there at this very small point where there is a very, very high pressure. With such an anvil cell, you can make Raman studies or how a material is changing under very high, very elevated pressure. That is very important, that is very informative. Because experimentally, that is quite simple. You just put this anvil cell under the microscope, and because it is very small, in this very small position, you can have a huge pressure, and it is easy to handle. And then you can study what happens to a material as you increase the pressure. And here you have a study mainly from inorganic chemistry, but it's totally relevant to catalysis or anything, which is the compressibility of different solids, in particular rare earth vanadates, from terbium and from dysprosium vanadates. So they are increasing the pressure all the way up to 5 gigapascals. And based on the shifts of the Raman bands, they can tell the compression, the shrinkage of the unit cell. So that the unit cell that was originally at atmospheric pressure with a volume of 1, as you are increasing the pressure 2, 3, 4, 5 gigapascals, this unit cell is compressed to about 3% smaller than its original size. Now you can see that the effect is discrete. You are going from 1 to 0.97. But you clearly see from this data, from the trend, that the plot is very nice and it's very accurate, and you can really measure how this unit cell is being compressed. And experimentally, that's very convenient, that's very simple. It's a benchtop system, it's a Raman spectrometer looking at that. And this paper was made in 1992. So that means that almost any basic Raman system of the 2020 will be able to do what a 1992 Raman system was doing, because in the last few years, you will see in a moment, Raman spectrometers quality has increased exponentially. I mean, I'm not exaggerating if I tell you I can have a Raman spectrometer in my pocket, because right now there are Raman systems that can fit into your pocket, and not in a big pocket, even in a small pocket, very small pocket. The other information that you can also get from Raman, which is also structural, is about what happens with the crystalline phases as you increase pressure, because one of the things is that the cell will compress, But the cell has a given structure. You compress, but at some moment in time, the crystal structure will change and something happen. So this is what you can see here, that not only looking at the shift of the frequency of the Raman peaks, you can tell a shrinking of it, but you also get the whole spectrum. And what you observe is that as you are increasing the pressure in this system, the frequencies are progressively changing. So all these peaks are progressively changing. Why? Well, because this unit cell is shrinking and shrinking and shrinking. So they are getting closer and closer. And so that's why actually all the frequencies increase, because everything is closer and closer. So the shorter the bond is, the higher the frequency. But there is a moment that everything changes. For instance, if you look here above 10 gigapascals, some of the Raman bands disappear, and a new Raman bands appear. New Raman bands appear here, here, here. So there is like a sudden change. Also here, for the higher frequency, you see that. Why is it happening? I'm making a question and I'm receiving a question from there. So make me the question and then I repeat the question.
So you are saying that the volume of the unit cell will decrease when you increase the pressure.
Yes.
That we can capture from the Raman.
Yes.
We can also get this information from the XRD.
You can, if as long as it is big enough to generate X-ray diffraction pattern, because otherwise you will not be able. And if you're looking at a material which is not crystalline, you won't be able to see that in X-ray. So these kind of things you can see with X-ray, indeed, because there will be a shift in the diffraction pattern associated with the bond length. But in this case, even with amorphous material which is suffering under pressure, you can tell. Or if you're dealing with crystallites below 3-4 nanometers, you can also see.
So what is the typical particle size of this?
You don't really have a limitation in the particle size, because Raman, as long as you have a molecular structure, it will be reporting about it. If you have a large crystal or a nano crystal, it will report. Of course, when you are dealing with a nano crystal, it will probably be more defective, which means that probably the Raman bands will be broader. You may even get some additional vibrations associated with some defects that you can hardly see in a large crystalline system, because in a large crystalline system, the regular periodicity of the overwhelming amount of atoms will dominate the characterization. When you go smaller, surface effects, defects will be more apparent, but in the end you will see the same thing, like vanadium pentoxide, you will see vanadium pentoxide. But you may see a little bit more of defects, but you do see essentially vanadium pentoxide. So the size is not really critical. That's the nice thing of Raman. Even the minimum expression of a crystal will be already apparent to Raman, which is nice. Now my question is, why when we are increasing the pressure, there's a progressive change in the Raman bands? Okay, we know, because the system is shrinking and the bonds are becoming smaller and smaller because of the pressure. But then all of a sudden, many bands disappear and new Raman bands appear. Why? What happens?
The crystal phase is changing.
Exactly. If you put so much pressure, then it goes from one phase to another phase and another phase. These have not, at the moment of publication, these have not been made for these dysprosium and terbium vanadates. So they know that the original phase, the one which is present up to 10 gigapascals, was the orthorhombic phase. But they keep on increasing the pressure, and they found that there was a phase 1, phase 2, phase 3, and phase 4 as you increase the pressure. So that's why you see these sudden changes, because you change a phase and then these vibrations are no longer present because it's a new structure with new characteristic vibrations. Then everything becomes different. Okay, so we continue where we were. Those remotely haven't lost anything. So basically that's it. I mean, you increase the pressure and you change the phases. So this is what we can see with Raman spectrometry. Again, the great advantage is that you don't need a synchrotron, you don't even need an X-ray system, you can use it in your Raman very conveniently. In organic chemistry is probably one of the disciplines that really enjoys Raman spectroscopy, and that's good, because in organic chemistry is basically what is used to make most of the catalytic materials. For instance, here you have another interesting study which is about the solubility of a given system within another. In this case, we are adding titanium oxide within zirconia, in particular yttria stabilized tetragonal zirconia. Tetragonal zirconia is a phase of zirconia that exists at high temperature, because at the room temperature you have monoclinic one, But the tetragonal one is structurally more flexible, and for several ceramic applications, having tetragonal zirconia is convenient because it doesn't eventually break. Mechanical properties are better, and the presence of some yttrium stabilizes this zirconia. But for functional missions, this is some research from ceramic people I was working with. You need to add titanium to this system. Now, how much titanium can you add to the system that remains within the zirconia lattice? Well, we were looking at these samples with an increasing amount of titanium oxide, from no titanium all the way up to 28% titanium oxide on this zirconia, yttria tetragonal stabilized zirconia phase. So what happened is basically highlighted by these lines of the Raman here and there. This is the spectrum of the yttria stabilized tetragonal zirconia, so it basically looks like tetragonal zirconia. And as you are adding titanium, you see that the spectrum looks similar, but it's not exactly the same. Actually, if there was a peak here at about 270, it shifts to higher and higher and higher frequency, and then it's not changing anymore. So there is some kind of progressive change, and then it levels off. And the same thing here with this peak. It changes a little bit, and then essentially remains constant. What is this telling us? Well, this is telling us that we are adding titanium, and the titanium is indeed getting within the zirconia phase, and that the zirconia is somehow accommodating this titanium within the lattice. So there is a progressive shift on the vibration modes telling you about this. If you plot these frequencies of those two peaks I told you, you will see how there is a progressive shift in these frequencies until above a given loading, 15 weight% titanium oxide loading, there is no more change. Why there is no more change above 15 weight%? Okay, we are studying solubility. So this is the maximum amount of titanium that the zirconia can host. You are adding more, and titanium says, sorry, no vacancies. So what happens with the new titanium? It just stays outside of the lattice, on the surface. Then any additional amount of titanium is no longer being hosted by the zirconia. So the zirconia is no longer accommodating. It's enough. We got too many titania. That's it. So basically, the additional titania goes nowhere, stays outside on the surface. And if you put even more titania, you will start to see the Raman bands of crystalline titanium oxide, anatase phase, typically. So this is basically reporting you that you have already reached the solubility limit. And if you put more, then there was segregated titania. So that was part of it. And of course, we were looking at different synthesis methods where you could go beyond this limit, but apparently that was the limit of solubility of titania within the zirconia lattice. There are many works, and I really wanted to show you something else about this, which is very important, but I will wait for a few more days, but I wanted to anticipate now. Raman spectra can be calculated. Infrared spectra can be calculated from computational chemistry. We have been working, for instance, on the synthesis of zeolites, and one of the tasks that we are doing there is there are two groups working on modeling the structure of the zeolites and the Raman spectra of the zeolites. We have been working on the synthesis of a different kind of zeolites within a European project and with a chemical company, Haldor Topsoe. And we have been monitoring this with Raman and at the same time making the calculations. So here you have another work from other people, which is already published, about the calculated Raman spectra for zeolite materials under different conditions. So you can see that there are many things that can be calculated, and for instance, there are shifts, there are differences between the experimental and the simulated spectrum, but you already start to get quite a good correlation. And in our case, we managed to get even much better correlation than what you can see here. But in the end, Raman vibrations are associated with the rings of the different silicon, oxygen, aluminum atoms within the different kind of matrices of the material. Real-time spectroscopy, you see that I'm dragging the jumping into operando, but there are many things. Raman per se, characterization per se is important, in situ is important, operando is important. I want to go little by little, because if I begin with operando, that was the end of the course. So operando will be coming in due time. And so there are many things that we can do, and you will see during these days with Raman spectroscopy real time, because the nice thing is that you are taking spectra within seconds and minutes, so that's pretty much real time monitoring. And we can make temperature programs in situ studies. You can make operando Raman studies with online activity measurements by gas chromatography, mass spectrometry, infrared gas analysis, whatever. Or you can even monitor liquid phase reactions. We will be talking about these things. The simplest thing, and probably my entry gate into the Raman studies, was just by playing with temperature. And that is relatively easy, because basically what you do is to increase the temperature linearly, stepwise, whatever. And you are taking spectra on the sample with controlled environment, with the controlled temperature, but you are using an in situ cell. An in situ cell, which is not an operando cell, you are not going to make reaction there because there's a lot of weight volume. It doesn't look like a catalytic reactor. It's not a catalytic reactor. It is an in situ cell, but an in situ cell is already telling you a lot of things about the state of the sample under controlled conditions. So conceptually, the in situ cell looks like this. Commercially, it looks like that. We put it under the microscope of the Raman system, and basically you have this window to look into it, and when you remove the lid, basically you have that, a lot of void volume, so all the gases go through it, and the environment inside the cell is controlled. And in this little well, you will put your sample as a powder, or maybe as a platelet, or wherever can fit there, which is only like a 4-5 millimeters diameter. And the outside body can be refrigerated by water, because these cells can go all the way up to 1,500 degrees C. So, I mean, temperature is not a limitation. Other cells begin at liquid nitrogen temperature. So you can characterize samples quite conveniently just with a Raman microscope and with an in situ cell from liquid nitrogen all the way to 1,500 degrees centigrade. And you can do many things. This is a nice paper, actually it's coming from the nanotoxicity people, but remember that everything connects. The other day I was telling you, toxicity of nanomaterials is basically because a reaction triggered by nanomaterials with our body, and this is catalysis. And what people is doing in toxicity is very relevant to us. I was telling you the other day, silica has very few hydroxyl groups. Typically, when you are talking about this surface, silica has about a hydroxyl per square nanometer, the fumed silica. And other oxides, other supports have up to 6, 7, 8 hydroxyl groups per square nanometer. So they have a much better dispersion capacity. But silica can be prepared by hydrothermal synthesis, and it will be highly hydroxylated, it will be more like that, or can be like fumed silica with very few hydroxyls. Or what you can do is a Raman study increasing the temperature of a precipitated silica. Precipitated silica is made by hydrothermal, so it will be quite hydroxylated, and then what you can do is to increase the temperature and see what happens with this silica and compare with silica prepared at very high temperature. Now, what is happening is that this precipitated silica has a good number of silanol groups. We already saw yesterday that with deuterium you can confirm that indeed this is a hydroxyl group. And over there is nothing with hydrogen, because those didn't change with the replacing of hydrogen by deuterium. And these are essentially associated with siloxane groups, silicon, oxygen, silicon rings. Different size, different characteristics. So typically, Raman spectra of silica looks essentially like that. How big, how intense are these peaks depends on the temperature history of the silica. And a fumed silica, which is made at 1,000+ degrees, looks like this, with hardly any silanol groups and strong bands at 600 and 495. A normal silica prepared by precipitation, more hydroxylated, will look more like this, having some hydroxyl groups, and these things are changing as you increase the temperature. And as you increase the temperature, you lose hydroxyl and you start to form bridging oxygen like this, so that in the end, you have many hydroxyls, all these surface hydroxyl groups, vicinal, geminal, or isolated, start to disappear, and basically you are going into this kind of rings at the surface. And that shows up by the increase of the bands over here associated with the rings. And in the end, a precipitated silica may look very much like a fumed silica, because just by doing very, very high temperature, things are going back. So this is interesting. You can also look at reversible changes. Changes are not necessarily irreversible. If you dehydrate the silica, even if you try to hydrate, and over here we will also rehydrating, you restore, but partially. But you can have completely reversible system. This is nickel molybdate. And nickel molybdate typically is known to have an alpha phase. Usually, typically, alpha phases is the first phase that people were finding because of room temperature on the table. And then people will start messing with temperature, whatever, pressure, and then they discover beta, gamma, delta, or orthorhombic, whatever. So in the case of nickel molybdate, the typical phase was alpha phase, which looks like the spectrum at the bottom. But if you increase the temperature, you will see how this phase progressively changes to another phase. And if you look at the 700 degrees centigrade Raman spectrum, you see something that looks different. This sharp peak from the alpha is no longer present. You get another different peak here from the beta phase. You get this other peak that is not exactly like that one, and a new peak here that is not present before. And this present from the alpha is completely lost. Now, you are going from the alpha to the beta phase. Oh, okay, I have beta phase. Okay, cool down and come over. Professor, this is alpha again, because this is a reversible change. So after you cool down and you look at it, oh, it is alpha again. So it's something that you cool and you get the beta. So you heat and you get the beta, and then you cool and you get the alpha. So some transitions are reversible, others are irreversible, but you can see that real time. Okay, another aspect that is more important when it comes to catalysis is the state of the supported oxides, whether it is hydrated or dehydrated, because we have moisture here in our environment, but we have water during reaction. You are making oxidation, and then in the end, paraffin will go into an olefin, into a carbon monoxide, carbon dioxide, and water. Or many reactions you are feeding water to some extent. So the vapor pressure is always there. You are never in a water-free environment, very rarely. Some reactions are absolutely anhydrous, but in very many cases you do have water vapor. That doesn't mean that the sample is wet, because running the reactions at 1, 2, 3, 4, 500 degrees, you cannot be wet. But there will be some interaction with the water molecules, and that is something that we have to know. So here you have, for instance, Raman spectrum of vanadium oxide on alumina. And for instance, there is something interesting that we will comment in a couple of days. The vanadium mode at very high temperature is about 1012. As you increase temperature, the vanadium mode decreases to 1003. So there's a red shift as you increase the temperature. Interestingly, for a given temperature, if you increase the partial pressure of water, you also see the same effect. So there is some interaction between the water molecules in the vapor and the oxide that somehow weakens this vanadium bond. So something is happening that makes the VO weaker. And that is something interesting to keep in mind, because water is produced in very many reactions, or is even fed in very many reactions. The Raman spectra, I've told you already, but basically this is the vanadium mode, VO, and for the higher loading samples, you also get the VOB, bridging oxygen, about 800 or whatever. And also, at lower frequencies, you will get bending modes. So the 1000 is like the stretching mode, but then you get the bending mode, something like doing like that. Well, the frequency for this bending mode is basically down here at about the 300. You see the VO bending is 330, which is the band that you observe here. So this band is the bending of this stretching. Okay? Fine. Similarly, if instead of vanadium you are looking at molybdenum, is very similar story. Here you have ambient hydrated samples 1 and 5 weight percent, and the same samples at 1 and 5 weight percent. You see that hydrated looks very different than dehydrated. In the hydrated with low loading, it has this band. Hydrated with high loading, it has even more bands, so that you see like more polymerization, because you also see the moly, oxygen moly vibration. For dehydrated, basically you see what I was telling you before, that the oxo group has a higher frequency as you increase the polymerization from 1 to 5 weight percent. This is on silica, and this is also on alumina. In the end, you get similar trends. Hydrated, increasingly polymerized as you increase coverage. Dehydrated, increasingly polymerized as there is a coverage. But even when the things look similar, they are not the same. And people was typically confused because they were not aware about how important ambient moisture is. And they were looking at this, or they were looking at that, and they didn't really realize that they were looking at the same sample but with a different degree of hydration. So people say, okay, the band is somewhere between 950 and 1006, and they were happy because they didn't know about that. Or sometimes it was ambient conditions, but the spectrum didn't look like this, but like that, because they were using a very, very powerful laser power. And with a very high concentrated laser power, the sample was very, very hot. So all the water was removed. So people didn't know about those things. And because things look relatively similar, people didn't really realize that things were exactly different and how important the moisture is. And we will come into the effect of water in a moment. But all the molecules, water, methanol, whatever, will have an interaction with the supported oxides. If you are flowing methanol, and methanol is important because there are major industrial processes producing methanol or converting methanol into formaldehyde, dimethyl ether, or other applications. So the oxidation of methanol is a major industrial process, and molybdenum, vanadium are active catalysts for that. So if you look at molybdenum oxide on silica, the Raman spectrum of silica is these bands over here, so forget about those and concentrate on the moly. Supported molybdenum oxide will have this molybdenyl bond at about 980. You are running methanol oxidation, and then when you look at the catalyst, and wow, spectrum is changing. Why? When you look at the spectrum and you see something like these new bands, 840, 770, so the dispersed molybdena during reaction, because of the presence of methanol, is losing dispersion, is aggregated into nanocrystals of molybdenum oxide. This is beta molybdenum oxide, which is a low temperature phase that was not known before of molybdenum oxide. If you keep on increasing temperature, this beta molybdenum oxide will go into these other bands, 816, 919, and so on, 284. That corresponds to the alpha molybdenum oxide crystalline phase, which is the most well-known of molybdenum oxide. So things are really affecting. The catalyst is changing. We are not doing operando yet, but we already see that if you make in situ studies during reaction, you see how the reaction conditions are changing the catalyst, and things start to look different. I forgot to say the day before yesterday, but I remember now. If you have any question or any doubt, please raise your hand and make me a question while I am talking. And for those at the other side of internet, please type on the chat, because Rajendran will be looking at it and he will raise his hand for you and make the question. So please feel free to ask things during my presentation, because sometimes it's much better to give an answer at the moment that you have the doubt, when we are still within the reach of those slides, than waiting for later on. You're not interrupting me. That actually I like it, because it really helps me to better convey the message or explain whatever it is. So please, any question, any doubt, type it from remote or just raise your hand from here. Okay, so this is changes that we're observing, and we're still not doing operando, but we're already in conditions which are relevant to catalysis. We are making reaction in situ studies. It's an in situ study where we are mimicking the reaction conditions. We're feeding methanol and air, and we already see changes. Now, the most important question that is arising and is present is water, because water is everywhere. How important is water? Very important. We already know that supported oxide, I've been showing you, is dispersed on a support, it can be like vanadium like this, and a support like titanium will have hydroxyls, and we already know that the titanium will react with these hydroxyls, and then we will get titanium oxygen vanadium bonds until we run out of available hydroxyls. The more vanadium we have, the less hydroxyls remain, and also the vanadium will not only be isolated, but it will be polymerized. And if we put more and more and more, in the end they will rearrange into crystals, nanocrystals, and then we will get, for instance, vanadium pentoxide crystallites. And because the monolayer is no longer a monolayer and they aggregate into something like that, part of the surface will be exposed again, so you will see another hydroxyls. Now, this is what I've been telling you all these days, but this is because we are looking always at dehydrated samples, means samples that we have at 1, 2, 300 degrees C in air. So we don't really have much important influence of water. But what happens under ambient conditions? Well, under ambient conditions, the samples are really wet. And wet means that the particles, even if you look at your sample, looks like a loose, dry powder, it has an ocean at the surface. It looks like a planet, like planet Earth with its layer of water. Our nanoparticles is the same. Don't think of them like something dry when you have them in your hand or in your bottle or in your vial. It's actually like an ocean. You have layers of water. You have molecular water, not hydroxyls. You have liquid water. You have an ocean at the surface. And what happens there? Well, that was a big question, and was already telling you before. that people was not really aware of that. And that's fundamental, because understanding a supported oxide, ignoring something that has a dramatic effect on the species, because okay, 980 to 1000, but 20 Raman shift different is quite a bit. So that is very important. So there was a work made actually by Gautam Deo, who is professor at IIT Kanpur, with Israel Wax, where basically they were investigating that kind of an effect, and you will see it in a moment. So you remember, hydrated, dehydrated, we do see a change. Dehydrated, I already told you the structure. Here you have, for instance, molybdenum oxide on alumina, dehydrated, the molybdenum oxygen double bond, and the molybdenum oxygen molybdenum bond. This is the stretching molybdenum, this is the bending molybdenum. Okay, fine. But what is this? Ambient, hydrated. This kind of models I was drawing yesterday, it's good. You have the support, you got moly here. This is a stretching at about 1000, bending, so that will be the stretching at 1000, the bending will be like 200-300, and then you get also the moly oxygen support or the moly oxygen moly. Okay, dehydrated, this is dehydrated. But what happens if you put water and then you go into the hydrated phase? Well, yeah, we have the spectrum here. What are these? Yes, sir. Okay, in this case, because this is only one oxo, you only have one possibility. It will be symmetric. If you have two oxos, like oxo here and oxo there, it can be symmetric or can be asymmetric. But with a single one, it will be simply stretching. And that is a very good question, because if you look at this vibration, it has the same frequency, and if you make an isotopic exchange with oxygen 18, basically you will see like this vibration is appearing at 1005 or at 980, depending on whether you have oxygen or oxygen 18, because the reduced mass, but you only have with or without isotopic labeling. So you have this or that, and progressively this one will decrease and that one will increase until there's nothing here and everything is there. If you have a dioxo, and you get oxo here, oxo there, and the metal here, for instance, molybdenum. Now, in this case, they may vibrate on the same way, which is symmetric, or differently, which is asymmetric. And then, when you're doing isotopic labeling, you have many variabilities, because here it's yes or no. But here you can have no, no, yes, yes, no, yes, yes, no. So, and then you have symmetric and antisymmetric, and then you go from one going into another into very many peaks. So there are many ways to see that. Also, when you have symmetric and antisymmetric, if you look at Raman, like symmetric will be stronger than the antisymmetric, and if you look at infrared, the antisymmetric will be stronger than the symmetric. So even if you use Raman and infrared without isotopes, you already see things. Of course, if you look at that, in Raman it will look like this, and in infrared it will look like this. It will be the same. So the question is very important. It really helps discriminating many things. But in the case of a monooxo, you won't have that difference. So Gautam Deo, he was doing Raman spectra of supported vanadium, supported molybdenum on different supports at different concentrations. So you have molybdenum on magnesia, vanadium on alumina, vanadium on titania, vanadium on alumina, vanadium on zirconia, vanadium on silica. In all these spectra, basically what you see is, as you go up, an increasing loading of vanadium on the given support. And you see some trends, like the vanadium mode appears to go to higher frequency, appears to go to higher frequency. At about 800, you get more bands of the polymerization, about 800 more bands. Okay, you see things. But what was happening exactly, that was the great value of this work, which is, I think, revolutionary, because basically it was explaining everything. How many of you have studied analytical chemistry? You did. Okay. In analytical chemistry, you remember these plots, which is logarithmic of the concentration of a component against the pH for the different solution chemistry. These kind of plots. This is the pH from 0 to 14, and this is the logarithm of the concentration. And here you have the phase that dominates the liquid phase, in this case for vanadium, and you have the same kind of phase diagrams for molybdenum, for tungsten, for chromium, for everything. And basically what happens is that when you go to very acidic pH, you have essentially monomeric species like this species down here, and as you go more polymeric, you start to get more oligomeric like V3, V4, V2, whatever. Now, all these species are fully characterized by Raman. And what Gautam and Israel were doing is to look at all these supported vanadium samples on different supports with different concentrations. Why different concentrations? Because by changing the concentration, you change this. How many solute molecules do you have per milliliter? And by changing the support, you have a setting on the pH, because supports like magnesia are more basic, supports like silica are more acidic. And then what they found is that basically the vanadium compounds that you were obtaining on supported vanadium oxides was essentially determined by the pH and by the concentration, liquid phase chemistry. And that was demonstrating that under ambient conditions, these species are totally dissolved. And you have a liquid phase chemistry. So basically you have an ocean, and what you get from the Raman is an information about that liquid phase. And of course, some people was using a very powerful laser. The sample was getting heated on your sample, water was evaporating, and it looked like dehydrated. They didn't know, they didn't care. They were not aware of this. And with this paper, the community really became aware of how important is something like the presence of moisture. And the same thing applies to other elements like tungsten, molybdenum, chromium, rhenium, etc. So they were doing all this work looking at different supports that provide different acidity, which at the same time is the medium on which you will have this ocean, and different dissolve, which will be the solute. So you will have the dissolved not only vanadium, but rhenium, chromium, molybdenum, and tungsten. And liquid phase chemistry is always applying. Here you have the different compounds and the most characteristic Raman band for these compounds. Well, this is what happens. And this is the reality. So that is a very important thing that you have to be in mind. Yes, sir.
So when they're doing the pH, for example, if it is a solution, we can use the pH meter to find out the pH of the solution. But when it comes to the support, so are they talking about the basic sites of which is present over the surface, or the?
Good. That's a good question. When you go down here, basically, the Raman spectrum was already telling you what was, basically it's telling you that on a support that was more basic, for a given concentration, compounds were more in this area. And for supports that were more acid, for a given concentration, the compounds were more on this area. So depending on whether you're more on an acidic support, a neutral amphoteric support, or basic support. So you don't get an exactly well, you can get the pH, and then but even directly through the molecular structure of the vanadium or molybdenum or whatever, it is already telling you, okay, I'm here. Because I'm getting this kind of structure, you are in this range of concentration of pH, or have that structure, I'm in this range of concentration and pH. So
Based on the species what they are observing by Raman, they are telling what pH it could be.
Sorry, I couldn't understand.
So based on the structure, what is present. For example, VO2 plus.
You mean, for instance, here or here?
Next
The phase diagram.
yeah, phase diagram.
Okay, fine, here.
pH2, which is corresponding to VO2 plus.
Down here, acidic and.
If we have this structure, for example, VO2 plus, then we can say that the support is existing in the range of 0 to 2.
Yeah, well, you will. Yeah, I mean, because you have the two variables, the support and the pH. But with this kind of structure, you won't see on a very basic support, because these, I mean, no matter the concentration, these things exist at a rather very acidic medium. So if you're on top of magnesia, you're not going to have that, because magnesia will not allow the system to go down to that acidity. Even when vanadium is acidic, the presence of the magnesia support all over the bottom of the ocean is basically imposing a more basic medium. So yeah, it's an amazing work. And we can also use Raman just to heat the samples and decompose a precursor. These are like a precursor, organic precursor of vanadium pyrophosphate. You have like organic ligands, which have like CH vibrations, carbon-carbon vibrations, and then you can heat this material. And when you are doing the decomposition of this material as you increase the temperature, basically what you are doing is to burn away the organic components and to evolve into the phosphate species, so you get the weak bonds there, and then something remains there. These two bands, about 16 and 1300, correspond to amorphous carbon deposits. So basically, by treating this precursor on a support, which I believe it was alumina, and basically what you are doing was to decompose all the organic precursors, leaving only the vanadium, oxygen, and phosphorus compounds, in addition with a little bit of carbon deposits, polyolefinic carbon deposits. Basically, this is coke. Raman bands at 1300, 1600 that look like this, kind of like a McDonald's. This is typical of amorphous carbon deposits. Now, you can do more things. We have been heating, but if you are heating in air, if you are heating in helium, why not heating in hydrogen? Why not heating in methanol? Why not heating in many things? Because then you can see what happens under relevant reactive environment during oxidation, during reduction, during oxidation. Do we make a break now or continue? It's about 10.
You need another 10 minutes?
I can be done in 3-5 hours and then have the coffee, or...
We can take a break.
Okay, this can be a story of... Well, that's Titania on vanadium is an interesting story. Maybe I can tell you that and then we go for the coffee.
Okay, sure.
Okay, so we can see things that are more relevant to catalysis. And one of them is a system which is vanadium oxide supported on titania. It's a very extremely catalyst used. Oxidation of the silane, environmental catalysis for remediation in NOx. Vanadium oxide on titania is everywhere. And you have a huge amount of papers because it's a very important system from academic point of view, from the industrial applied point of view too. Vanadium titania has a problem. Typically we are using titania anatase. Vanadium titania catalysts sometimes they deactivate because they go into the rutile phase. You know the crystalline phases of titanium oxide, anatase, rutile, brucate. Okay, so anatase and rutile, to go from anatase to rutile, you need like more than 1000 degrees. However, these vanadium titania catalysts deactivate into the rutile phase at about 600 degrees, way before you should have anatase to rutile transition. Why? Well, because the active guy, the vanadium, is also a problem, because vanadium may eventually get into the titania lattice and trigger the anatase to rutile transition at significantly lower temperatures. Now, this is a rutilization triggered by vanadium at something like 500-600 degrees centigrade. Here you have a family of vanadium oxide on titania, Raman in situ dehydrated spectrum. Bare titania looks like this. You get these peaks at about 500 plus, 500, 390, 160, and 140 plus. This is a very strong peak, and this is the very most characteristic peak of titania anatase. You can put vanadium on top of titania, and under dehydrated conditions, you will get dispersed vanadium. Very little at the beginning, but Raman is sensitive. If you blow up this little thing, it looks like that. It's a nice spectrum, 1 weight % vanadium oxide and 99% titania. You see that. And what you see? A vibration at about 1000 plus, which is this vanadium mode of the dispersed vanadium oxide on top of the titanium anatase support. You increase the coverage, okay, you have more and more and more and more vanadium, so this band grows stronger, stronger, and stronger. And because you have more and more, they start to have neighbors. They start to have vanadium, oxygen, vanadium bonds, and then you see an increase in polymerization. This was isolated. This is probably isolated. Here you start to see the polymerization increasingly polymerized. So this is 5 weight % vanadium oxide on titania. If you put a little bit more, you start to get new Raman bands, sharp, intense, elegant, slender, crystalline phases of what? Vanadium pentoxide. So you have the dispersed vanadium, and next to it, vanadium pentoxide nanocrystals. You see this band at 990, you see this band here, you see this band there, you see this band there. So you see vanadium pentoxide. How much? Hardly a little bit. But even when this is hardly a little bit, because you still have a little bit of dispersed vanadia. So we have put very few more, from 6 to 8 weight percent. So you have the minimum expression of a vanadium pentoxide crystal, and you can already see it pretty nicely, very sharp, elegant peak, because Raman is extremely sensitive. You are at a moment that X-ray will never realize that there was vanadium pentoxide crystals there, but you see them with Raman. But the interesting thing here is not really what happens with vanadium pentoxide, but this is important because I wanted to highlight how important is also Raman to detect molecular structures at very low loading. So this is the fresh catalyst before reaction. We were using this catalyst for ethane oxidative dehydrogenation, which means ethane and air to make ethylene. 500 plus, 600 degrees centigrade, and the catalysts look very different after reaction. The same family, this is like before going to catalysis, after going to catalysis. They are totally different. Why is that? Well, I mean, the titania doesn't really change. Before and after reaction, titania anatase is titania anatase. 1 weight percent vanadium oxide on titania, well, the titania looks pretty much the same, but you don't see dispersed vanadia anymore, or very little vanadia anymore. So somehow the surface vanadia is no longer there. Why? Where did vanadia go? Did it fly away? What happened with vanadia? It went down, exactly. It didn't fly away. Other systems you may fly away. With molybdenum, sometimes you get molybdenum oxohydroxides that evaporate and are lost during reaction, but in this case, no. Vanadia doesn't fly away. Whatever happens is that it stays there and sinks into the titania lattice. And that is resulting in this big problem. Like you already see like something different here for 1 vanadia titania. You lose the surface vanadium and you see something here. 2, 3, 4, 5 weight percent titania, basically you no longer see the vanadia. And what you see is that the Raman spectrum, Raman bands of the anatase phase of titania disappear. You get something different here. And what you get here is actually the Raman bands of rutile titania. And vanadium is simply disappeared. It's not apparent to the Raman spectra. Why? Well, Rajendran said, it gets into the bulk. And what happens? Okay. So that was it. It was dispersed and it was crystalline. And in this case, basically, what we have is this rutile phase, and the vanadia somehow has got into the structure of titania. Of course, titanium is titanium 4 plus, and the supported vanadium is 5 plus. So if you have like a titania, which is a tetravalent, and here you have vanadium oxide, which is pentavalent. But at the end of the day, what is happening is that this, which is anatase, ends up like titania with some vanadium inside, which is rutile, and there is nothing here on the surface. Well, you will have hydroxyls or whatever, yeah, but no vanadium anymore. Okay? How can vanadia enter on the titania lattice? This is titanium 4. And will vanadium 5 plus enter here? Well, depends on many things. Essentially depends on the oxidation state. And so I want you to think about that, and also to see that I already say here vanadium 4 plus. So when vanadium is partially reduced from vanadium 5 plus to 4 plus, it grows a little bit in size. And the vanadium 4 plus has essentially the same size than titanium 4 plus. So for vanadium 4 plus, it's very easy to replace some titanium sites in the lattice. And that is the beginning of the end. Basically, by doing that, vanadium is catalyzing the transition of anatase phase to rutile, because vanadium substitutes titanium because they have a similar site but not identical. So it is substituting it, and by doing substitution, lattice is not what it used to be. It's a little bit more, and then you trigger the tendency to go into rutile at 600 degrees C and not at 1000 plus. So this is another kind of catalyst, a catalyst for the activation, but the catalyst anyhow. So we wanted to explore the boundary conditions. When you are doing ethane oxidative dehydrogenation, this is a redox cycle. And in a redox cycle, the catalyst is being reduced and reoxidized continuously. So you are feeding ethane, which is C2H6 plus oxygen plus argon or nitrogen or whatever on the catalyst, vanadium titania. So this catalyst reacts with the vanadium to make ethylene, and then when the catalyst gets partially reduced because of this, the molecular oxygen regenerates the oxidation state of vanadium. So somehow this catalyst is being reduced and reoxidized continuously because this is a Mars van Crevelen lattice oxygen. You were telling about that on the first day. Is being given, so this oxygen is going to react with this to produce water. So this oxygen comes from here, but it doesn't go directly. This oxygen is given to the vanadium, and the vanadium is giving a lattice oxygen to do this reaction. So it's a redox cycle going through the lattice. Now that means for a fraction of a moment, the vanadium is being reduced and reoxidized continuously. It's a redox cycle, reduction, oxidation. So let us go at the boundary conditions of a redox cycle, which will be heat under hydrogen, which is what happens if I am reducing, and heat under oxygen. What happens if I am oxidizing? Somehow boundary conditions. What is the redox cycle? I mean, it's not in hydrogen, it's not in oxygen, it's somewhere in between where the sample is being reduced and reoxidized continuously. But these TPR and TPO in situ Raman studies will tell us the boundary conditions. Let's look at the catalyst if we are heating it in air. TPO Raman, one of the catalysts, 6% vanadium oxide on titania. You remember there is dispersed vanadium and a tiny amount of vanadium pentoxide. Okay. You increase temperature, 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 you increase temperature. What happens? Surface vanadium is disappearing, yes. But if you look to the right, at the same time that the surface vanadium is disappearing, you start to see that the Raman bands of the titanium anatase are becoming less and less defined. And then above 600 degrees C, it no longer looks like anatase, it looks like rutile. So basically you see at about 600, 650 degrees C that the anatase goes into rutile just by heating in air. But remember, this is a redox cycle where the catalyst is being reduced and reoxidized. Now let's look at the other boundary condition. What happens in the extreme case of reduction? We flow hydrogen, and we are heating hydrogen, and then the sample will be reduced as we heat. Look at vanadium. Here you have vanadium. And as you increase the temperature, this vanadium decreases, decreases, decreases. You don't see vanadium anymore. But if you look at the right side, titania remains like anatase. You don't have a change to rutile. What happened to vanadium now? Well, we have hydrogen. We are reducing the vanadium oxide. And by reducing the vanadium oxide, we avoid the anatase to rutile transition. Why? What's happening here? What is the trick?
It's no longer P4+.
Exactly. It goes down to? It goes to 3+. And that is it. If you look at the temperature, TPR, temperature program reduction in hydrogen, this is what you get. This is the hydrogen consumption. Of course, you make a TPR of titania, you don't really see much. You make a TPR of vanadium titania, you will see a reduction. Maybe 400, 415, 420, 450, whatever. Depending on the coverage, the reduction of vanadium occurs at different temperatures, but anyhow, in the region of 400 to 450. And what happens during that reduction? Well, basically, it goes from vanadium 5+ to vanadium 3+. When do we have the deactivation? Remember, heating in oxygen above 500 degrees, you start to get this anatase to rutile transition, which is triggered by vanadium 4+ migrating into the lattice of titania. Now, when we make a TPR, hydrogen reduces vanadium from 5+ to 3+. Before we are getting the temperature at which the vanadium 4+ would be able to enter into the lattice. So there is no chance for vanadium 4+ to enter into the titania lattice in hydrogen because it's already reduced into 3+. And what happens with the size of vanadium when it goes from 4 plus, from 5 plus to 4 plus to 3 plus, when we are talking about the size of this cation? Exactly. When you reduce it, it becomes bigger and bigger. So, typical conditions, if you heat in air, vanadium 5 plus goes into 4 plus, which is a little bit bigger, but just the size to replace titania. And ultimately, this will trigger a solid transition from the anatase to the rutile. But if you heat in hydrogen, vanadium will be reduced to 3 plus before there is chance to diffuse into the lattice. And then above 500 degrees C, sorry, you're too big, you cannot enter, stays outside, and then the anatase doesn't die into rutile, and the vanadium doesn't sink into it. It's simply stored there. And now this is like a key message, because actually if you realize this is something very interesting, and then during catalysis, what is happening? Are we in air? Not exactly. Are we in hydrogen? Not exactly. What are we doing during catalysis in ethane ODH? Well, we are doing a redox cycle. The catalyst is being reduced and reoxidized. So we are not totally in oxygen, we are not totally in reducing conditions, we are in between. Chances to go through vanadium 4 plus are high. And once that you're vanadium 4 plus, you fell into the titania. And then you start triggering this transition. You are doing two things at the same time. Getting into the titania lattice and triggering the transition from the anatase to the rutile phase. By doing that, you are making rutile. And they say, oh, my catalyst is deactivated because it is rutile. And then the people has the idea, rutile is bad for catalysis. No, not exactly. The problem is not that rutile is bad for catalysis. If you disperse vanadium rutile, it will work fine. Actually, Gautam and Israel made a paper about that, and that is not the problem. The problem of rutile is not rutile per se. Is that if you see rutile, means that you have lost all the surface vanadium. And if you lose the surface vanadium, you are losing the guy who is doing the job. So the problem is not rutile per se. Rutile is an indication that you have lost the dispersed vanadium oxide. And this is a very interesting message. Long before we are making operando, we already see that the catalysts are very dynamic. They change. Many things change during reaction. It's not the same heating in air that heating in hydrogen, that heating in reaction. In air, you will heat and the catalyst will be like this. Kind of getting hot, but that's all. You heat in hydrogen, the catalyst will be reduced. And okay, something happened. But if you heat in catalysis and the catalyst will be working, and in this thing there are more chances for structural changes. And that's why the operando study is very important, because the catalyst is a lot more busy. It's not just studying, looking at the molecules passing by. There's something else. This triggers the reaction. That's why it's so important to get into the real reaction conditions.